Hello everyone. In this video, we will be looking at a rectangular slab uh, next to an insulator and exposed to bulky air and explaining in mathematical terms how this temperature will evolve over time and sketch a temperature profile so that we can visualize this change in temperature. So let's quickly go ahead and make this system. So we're going to start by making the slab as such. Now, for our initial conditions, we're told that uh, uniformly it is uniformly 80 degrees Celsius. So what I'm going to do is write down and say that at temperature at X at T or time equals 0 equals 80 degrees Celsius. So we have that as an initial condition. We're also told that one side is perfectly insulated, so I'm just going to draw a quick little insulator on one side. And we are told that there is air with a bulk temperature of 20 degrees Celsius. So I'm just going to express this by drawing a couple arrows going up on this side, which is my air, at 20 degrees Celsius. So let's go ahead. We have to explain in mathematical terms how this temperature will evolve over time. So this this is kind of getting into this is common sense engineering where you can imagine if you have a slab that's insulated on one side and it's exposed to cold air on the other, it's going to steadily lose its temperature and become close to or at eventually that 20 degrees Celsius from the air. So how do we know that? How can we at least prove that or at least visualize it? Well, what we can do is say, okay, if we start with an initial temperature, we know that we're going to reach this cross-sectional area of the slab, which I'm going to put like this, and this is going to be met with the energy due to convection of the system. So it's going to absorb some of the temperature on that boundary. And what we're also going to say is that there will be energy leaving, which we're going to call oh, I'm so sorry. This is supposed to be conduction going to the boundary layer, and then we're going to have convection leaving this boundary layer. So before we begin drawing what these look like, or the equations for them, let's go ahead and state some more rules about this boundary. I'm going to say for this side, or over here, that this equals 0, and that this point equals L, and that the positive x direction, in this case, because we have to state that if we have our boundary layers, is going to be going this way. We're going to be going to the right. This will be very important when we begin mapping out our conduction and convection equations. So let's go ahead and start with our conduction equation. We have Q of conduction, which is equal to the thermal conductivity times the area multiplied by the temperature profile of the boundary, and this will be from 0 to L. So that is our first equation. Our second equation is going to be the convection. Convection, and this is equal to H times A, and then remember, we looked and said that x is positive going this way, which means we have the distance of infinity in this case. So like this could be any distance. I'm just going to say that this is T infinity, and we have the temperature of our surface, TS, over here. I'm just going to go ahead and put it over like this. And so if we're going from left to right, it makes sense to have our T infinity be subtracted by the temperature of the surface as such. Now, an important concept, if ever we have a heat transfer, the heat coming in must be expelled by the heat coming out. So there has to be a proportional relationship between conduction and convection. So we're going to actually set the two equal to each other to begin to visualize this heat profile or this evolution of temperature. So we're going to go ahead and set negative K A as such. Okay, so now that we have this equation, how can we apply some more common sense to make this profile? Well, if we're going to make a profile, we already know what the right side is going to look like. At any point, at any temperature, the slope on the right side will always equal zero. Well, why is that? When we have a insulator on the right side, we know that it's going to be the same temperature as the slab itself because it can't store any energy. It can just it's terrible at holding any energy. So when it's met with it, none of it's going to transfer over. So we can make an assumption that it will be the same temperature as the slab in this case. So we know that the slope to the right will always equal zero because of that. And so we already know what our right side looks like, and because of that, we can just say the slope on this side equals zero, just like that. Now, let's apply some more common sense. Let's say we want to make a graphical relationship between this side eventually going to that slope of zero. Well, let's go ahead and do this. When you have something cold be met with something that is warm, it very quickly heats up for a little bit. So we're going to have a pretty sharp slope. However, if you try continuing to heat something that's already being heated, you'll notice that it takes longer and longer to heat up. That's because the difference in temperature is getting smaller the more that you heat it. So there is actually a decaying relationship with how much it heats up until eventually it has heated up to the temperature that you've wanted. So as this continues, you'll notice that our line actually slowly, not that quickly, slowly begins to dampen until eventually I'm going to go ahead and make this green. We get to a point, and this is after a long time. So I'm going to say at T, let's see here. At T infinity, we have reached a point where at all times, or we have reached a point, it's been so long that eventually the slab has lost all of its heat, where this will now equal 20 degrees Celsius. Because eventually it's going to lose all of its heat. And so there's going to be a straight line relationship between the surface area of the left side exposed to the air and the insulated side. And so that is how we can sketch the temperature over time for this rectangular slab. Hello everyone. In this part of the video, we will be sketching a temperature profile of a quasi-steady state system. So, this system is going to be coffee in a glass cup surrounded by an insulator exposed to air. So, the point of this is going to be to demonstrate what convection and conduction look like for heating a system, and then we're going to go ahead and actually graph a temperature profile to show how in a steady state heat transfer moves throughout a system. So we're going to go ahead and begin by making our system. We're going to go ahead. I'll start off with just making a big ol' thing like this. And then I'm going to make my first layer, which is going to be my coffee. And now I'm going to have my glass layer. And then I'll have my insulator. And then I will have the air it is exposed to, which I'll kind of demonstrate with these arrows going up. So we do have a couple initial conditions. We know that the coffee is at a bulk temperature of 90 degrees Celsius. We know that the air is 20 degrees Celsius. Now, we also know that this is a quasi-steady state condition. So what does that mean? When we observe something like coffee in this sort of steady state, that means that at every point, no matter what, we are at 90 degrees Celsius. It is not going to deplete, it is not going to change. We are going to stay at a constant 90 degrees throughout our system. And what this also means is for anything conduction based, it's going to be a pretty linear relationship of heat loss overall as heat begins to travel through the system. But we'll explain that later. First, let's go ahead and start showing off some of the math of this problem. So, as we know, if we have uh, heat transferring from a fluid like coffee, this is going to be heat transferred via convection. And we're going to call this, let's call this surface 1. Now we have glass. This is a solid and it will transfer its heat via conduction instead. Call this surface 2. Now we have the insulator. Again, this is a solid, so we're just going to say that this is conduction. And for the air, just leaving, we're going to say that this is convection again. So, as stated in the first part of this video, whenever you have heat transfer, you have to consider the proportional relationship of energy entering a system and exiting a system. So in this case, we're going to make an equation here that states that the energy of convection equals the energy of conduction, which equals the energy of conduction, which equals the energy of convention. As you can see, this is corresponded to each part of each layer that we have. So how do we make the equations for this now? So let's go ahead and start to the very left. Let's start with the air over here. The convention equation is going to look like H times the cross-sectional area multiplied by, and let's see here. This would probably be a convenient time to make a positive x direction, which I guess we could do 0 length. Even though we're sketching even though we're just showing off a temperature profile, it's still important to note which direction of x is in fact positive. So we're going to say it goes that way. And if that's the case, we have the temperature of the air minus the temperature of surface 3. Sorry, 3. Now, this is equal to negative K, which is the thermal conductivity, times the cross-sectional area. And this is going to be the temperature gradient of this surface. And for this is going to be the thermal conductivity of the insulator instead. Now we're going to relate this to the thermal conductivity of the glass times its area multiplied by its temperature gradient. Then we're going to relate this to the convection of the coffee, which is going to be what? HA And this is going to be T coffee minus the temperature surface of 1. So here we have the mathematical relationship between all the profiles, and they all have to equal each other in this case. Because remember, whatever goes out, I mean, whatever comes in must also come out in a proportional amount. So how can we begin to sketch the heat profile for this? Well, this actually is a lot more common sense than anything, because if we make a little heat profile chart as such, let's say this is air, this is the insulator, this is the glass, and this is the coffee. I'm just going to go ahead and kind of lightly make these lines to help make a visual guide for us. Okay, so let's imagine it like this. If we are at a steady state and we are looking at coffee at 90 degrees Celsius, as stated earlier, our coffee is just going to stay at 90 degrees Celsius. So as we begin from X length temperature in degrees Celsius, we are just staying this same temperature at T equals 90 degrees Celsius. But as we begin to go through the glass, something else happens. So there's actually a pretty easy way to visualize this. If you imagine having a really hot liquid in a cup and touching it, it burns your hand. Why is that? Because its conductivity is actually pretty high. It absorbs a lot of heat. So this is going to be pretty high. And so the temperature actually really doesn't drop that much. It's still going to be pretty linear. It's going to be a linear line going down, but it's not going to go down by a whole lot because, again, it has a higher thermal conductivity, so it wants to hold more energy. This is different from the thermal conductivity of the insulator, which is much lower. This is why an insulator makes it so you can hold a hot cup because it's really bad at absorbing energy. So we're going to make this go much lower instead. And now this is like a temperature that you could actually begin to hold this and feel comfortable. And now when we're exposed to the air, even though we are in a steady state, that doesn't imply that the air in this case is going to be linear as well. Because unlike what is happening with the insulator and the glass, this is not in contact with either a conducting absorption force, and it is not in contact with the actual source of the heat. And rather, it's in contact with a different source of temperature, the air, which is at 20 degrees Celsius. So what happens is rather than linearly losing its heat, it's instead going to exponentially lose its heat. And it's going to get much colder. Oh, it's going to get much colder into a point until it's eventually 20 degrees Celsius. So that's why it's not very linear, and that's why it begins to curve like this. And that is the temperature profile for a coffee cup with coffee that is in a glass cup that is in an insulator that is exposed to 20 degrees Celsius air. Hello everyone. In this part of the video, we are going to go ahead and express the conductive and convective heat transfer process in the system that we had used in the previous part of this question. And we are going to go ahead and relate it to the thermal resistances of the system to then derive an expression for heat flow in terms of material properties and what is it? And dimensions. That's what it was. Sorry. So let's go ahead and begin. So when we observe our system, one connection that we made was is that the energy of conduction and convection are all proportional and equal each other. So let's go ahead and sub those equations in again really quick. Starting from left to right, we have the convection equation, which goes as times the area times, and this is T temperature of the coffee minus the temperature, which we're just going to call T1 for now. I'm not going to call it surface 1, which is equal to the conductive energy from the glass. So this is the negative thermal conductivity. Let's see here, multiplied by the area in regards to temperature 1 minus temperature 2, right? Now, let's go ahead and set this equal to the insulator. Or, sorry, hold on. Make sure that's thermal conductivity for glass. We'll do thermal conductivity for insulation. It's cross-sectional area of T2 minus T3. I don't know why I made this so wide and didn't space this right. Let me go ahead. Just gonna go ahead and move this over here. Scrunch it up a little bit. And then we'll go ahead and do the same expression for the convection of temperature leaving the air, which is h of air times the cross-sectional area, the temperature 3 minus the temperature of the air. Okay, well, we have this relationship. For the heat transfer process, we can go ahead and make three equations off of this. Our first equation is going to be setting uh, the convection equation for heat of coffee. We're going to set this equal to the conduction of glass first. I am actually going to go ahead and be a little lazy here. Okay, never mind. That didn't work the way I thought it would. That is unfortunate. I'll just have to write the whole expression again. Right. Derive second equation. Really, all I'm doing is just relating. I'm arranging these equations in a way where we would be able to use substitution to solve for these variables. Just kind of, if we knew one, then we'd be able to solve the other. So go ahead. Now we have air area is T air equals, and we'll set this equal to U. Solution area 2 minus T3. So here is the current problem, the current predicament that we faced with this equation. When you observe these three equations, there are too many unknowns for us to continue and proceed to realistically solve for any of these temperatures or thermal conductivities. We don't know the H of coffee, we don't know the H of air, and we don't know the thermal conductivities of the materials that we're transferring through. And we also don't fully understand the temperatures that are in between either. So we're left with a lot of unknowns. So you may be wondering, how do we proceed at this point? How do we actually go ahead and try to solve something here? So there is one very useful equation that we are going to write down that we are then going to derive an expression for and prove that this actually works. Oh, actually, all of these equations are set equal. I should probably state these are all equal to some energy or anything. That's really important for what I'm going to show. We have Q equals the universal heat transfer coefficient times an area times a change of temperature. So, what does all of this mean? This will be a way for us to relate all of these equations by some universal heat resist by some universal thermal resistance. And we're actually going to go ahead and turn to voltage as a way to show us how this relationship can be established so that we can eventually find all of the missing variables that we have in our question here. Go ahead. We kind of mentioned just like part two for this. So, as I said, we're actually going to turn to voltage to get some of our answers here. Let me go on a straighter line. Whatever, sure. So, change of voltage equals current times resistance. That's great. What do we do with this? Well, let's go ahead and look at something like conductivity. Conductivity, when you look at the equation, looks a little something like this. We have our change of temperature multiplied by, I swear I know what I'm doing. Uh, our thermal conductivity multiplied by the area, which is then set equal to some energy, right? So when you look at this, you can actually kind of make a lot of similarities. We have a change in voltage as we would a change of temperature for the conductivity. And if we set that equal to our thermal conductivity, our area, and our energy, we can actually see, and we can actually imagine our energy as the current to our system, therefore making our thermal conductivity per area our resistance, which, if you think about it logically, makes sense. Our thermal conductivity and area are both what determine how much energy something can be stored. In the same way, resistance is determines how much voltage you can have throughout your system. If your thermal conductivity increases, your change of temperature increases. I mean, your energy increases. Actually, yeah, yes, your change of temperature increases in the way that if your resistance increased, your change of voltage would also increase. Got into my own head there for a second. So let's go ahead and rewrite this. We're going to have our change of temperature set equal to Q times, uh, oh, we also assume that this is a change of temperature over some length, right? We're always concerned about the length for conductivity because that matters for our equation. Length over our thermal conductivity multiplied by the area. So that is this part of the equation over here is actually our thermal resistance. Though in the same way that you can imagine that this is the resistance for voltage. So now that we have it for conduction, spoiler warning, we can do the same thing for convection. I write down convection here. Convection. We can do practically the same thing. We have Q equals our H of A multiplied by our change of temperature. And we're just going to do the same thing. We're going to do our change of temperature set equal to our energy. And now look at that. We have our thermal resistance for convection. Resistance. All right, so now we have an expression for thermal resistance for both conductivity and convection. So, how can we actually implement this into our system? Well, what we can do is create essentially the total resistance for our system. So, think of it like this. We have a change of temperature for the entire system, so equal to the energy for the system. These two are always, I mean, we generically have already solved for them for the conductivity and convection. So now we're just going to go ahead and combine like terms. And now what we're going to go ahead and do is put 1 over area in front. We're just going to pull it out from these guys. And we're going to go ahead and apply these thermal resistances to our equation here from our coffee system that we have made. So if we start with coffee, this will look something like 1 over H of coffee. And now we're going to add that by the length and then the thermal conductivity of, let's say, glass. And then we're going to add that by the inverse of the thermal conductivity insulation. And we're going to do the same thing for the air. And if you look at this, if you know anything about physics, this looks really, really similar because this is actually really similar to the total resistance equation. Just kind of drawing it here for reference just because I think it's cool. But we get the total resistance. Total thermal resistance. So, how do we use this guy? Well, if we remember our universal heat transfer coefficient, this is actually how we derive this expression. So let's go ahead and take U and A. U times because of our 1 over A. Uh, the actual full setup for this portion of the equation looks a little something like this. R over total resistance, which we just solved for over here, over here on this side. So now that we know our U of A, this becomes pretty rudimentary because our change of temperature for for the system is just our temperature of the coffee minus the temperature of the air. Now, if you look, we now can solve for Q finally, which there's a lot of writing to get there, but yes, we finally we can finally get Q. Q equals U of A, which we know is this guy, multiplied by the change of temperature. So we spent all this time deriving this. Why is this useful? Well, now what we can do is individually solve for all the unknown variables that we didn't know. So let's say something like the thermal conductivity for insulation, area, T2 minus T3. Now that we know Q, do kind of like a checklist here. And I want a better color. I want green. Green means good. So now that we know Q, we can relate this to all terms. We'll be able to solve for the thermal conductivity. We'd be able to solve for the area and for the overall change of temperature, thanks to the equation that we have derived.